Welcome to our next session here in our gradient boosting chapter, and specifically to our part here on component-wise boosting. So here in this session I'll mainly talk about nonlinear base learners, discuss a few more advanced details so that we usually have to kind of follow a decomposition approach if you're using splines, so that kind of splines are not over-selected. We usually care about that specifically when we care about fair base learner and fair feature selection, because we want to interpret the model at the end. And I'll also discuss a little bit how we get our hands on partial dependence curves from the component-wise boosting model, and that we can also compute feature importance measures from CWB. So, as we already discussed, we can use nonlinear base learners. Usually these nonlinear base learners are still, if we care about feature selection, specified with respect to a single feature in our data sets. In many of the examples before, we have actually used linear base learners to keep the examples simple. We also had a dedicated session on comparing component-wise boosting to GLM models. So here we'll specifically now target spline-based component-wise boosting. So usually we use like a cubic B-spline basis. So we can model nonlinear effects nicely like this. Okay. Now, so far so simple. I think we didn't really look at that before in too many examples. This is why I'm doing this here. So again, we are using this life expectancy data here, again with the features adult mortality, BMI, country, and year. And I mean, I really went through the structure of this example and this visualization here in detail in one of the previous sessions, so I'll do this a little bit faster here. So we basically let the procedure run in a very, very similar manner. Now we have these nonlinear base learners on top of our features, and again, in each inner loop, we'll select the feature and the associated base learner with the lowest SSE when we fit against the pseudo-residuals. And here you can see which of these features was selected in a certain iteration, and here you can see how the loss develops over time. And here in all of these guys, you can see how the feature effects, this is also what we'll later call the marginal effect or the partial dependence curve, develop over time. In the dotted lines, you can see the current candidate models. And as at the moment, we are at iteration 0, so we just have included an intercept. Each of these effects in the model are 0, and the dotted lines are what we would add in if this base learner would be selected in this iteration. Now, in this first iteration, you can see that adult mortality is selected. You can also now see that as we are multiplying this with a moderate and smallish learning rate, this thing here begins to develop rather slowly over time, but you can see how this changes a bit from the 0 curve. And now we do this again, risk goes down. You can see how this is more and more, how this non-dotted bold line here, which is the current effect of our model, is affected more and more and more. Do this more, we do this more, we do this more. And you can also nicely see now how this adult mortality curve gets closer and closer to the underlying data. At some point, we do not gain anything by adding more partial spline effects to this feature. And now we actually begin to drill down on BMI here, add that in for a couple of iterations. Now country is added in. And for that, we didn't do anything special here because this is still our global categorical effect where we model all of the categories in one feature. And then we go on and go on and go on and go on. You can see here that we are now going back for some iterations to adult mortality. And at some point, I guess we converge. I guess we now have even added in some smallish updates to year spline in the later iterations. And empirical risk begins to flatline. And I guess at that point, we would stop. Now, in a certain sense, this was not anything new until now. If you would run this naively, you would pretty immediately see that you would run into problems here, because unfortunately these spline-based base learners are much more flexible than these linear parts. Well, and maybe you also want to kind of like have these linear base learners and in there for some features, or you would like to have non-linear base learners in there and linear parts, and maybe even have component-wise boosting select from these. Problem is, if you're doing that, the component-wise boosting algorithm will mainly select the non-linear stuff because it's pretty much obviously more flexible. So there's a proposed decomposition now to solve this problem. So usually what we do is we take apart our non-linear spline-based base learner into a constant term, into a linear term, and in a non-linear term. And this non-linear is kind of like a centered version of the spline, yeah? And it only captures the deviation actually from the linear effect. So if you will have something like this here, yeah, you would kind of take this apart into a linear part and a non-linear spline-based part. And there's even something else in there. So there's kind of a specific regularization procedure in there. So we kind of model only what is not, so we model only through the non-linear spline part what is not captured, or what cannot be captured through the linear part. I'll skip some technical details here because that becomes rather complicated. So here's at the very least a small simulation that shows this to you. So if we would not do this, so here we have used a pretty simple univariate function based on one feature x, so with a sinusoidal part and some linear part. And if we would now run component-wise boosting on top of that with our normal linear base learners and our uncentered non-linear base learners, you can see here the non-linear stuff gets selected 100% of the time. If we run the centered stuff, you can see that nicely. First, the linear part is selected, and only after that the centered spline. And we have now a nice decomposition. And we can even talk about, hey, this guy here, this reddish guy, represents the trend in our data. We can interpret that as well. And we have this nonlinear spline part, which tells us how much nonlinearity we need on top of that linear trend part. Unfortunately, even here, the technical extra things don't really stop and that we have to do. So even for this, there's still the problem of how much do we regularize the spline, because even after this decomposition, it can happen that the nonlinear parts actually get selected too often. This makes it problematic potentially if we want to talk about fair feature selection at the end. So what we usually do is we try to set the regularization of our spline learners based on the degrees of freedom. So we kind of match the regularization of the spline with the degrees of freedom of that spline, so that all of the degrees of freedom of all considered base learners are configured in a way that they are equal. Yeah. So the idea is to kind of allow for each base learner from our pool an equal measure of complexity. And again, for this, a little bit of more maths would, I guess, be needed. Again, this becomes technically a little bit more difficult, and again, I'll skip the technical details here and refer to the literature that we have linked here on the slides. So to wrap it up a bit, there is now a quite large number of potential base learners available to us. So you can either use linear effects, can use interactions, can use uni or multivariate splines, can use tensor product splines, could use trees, discuss them a lot more in the normal gradient boosting part, can use stuff like random effects, you can use Markov random fields, I can even boost functional covariates, and all of that can be handled quite nicely in this template algorithm of component-wise boosting. So because of this, we can really boost a huge class of different models and can handle a lot of different data scenarios here. So can even do stuff like even extensions to handle distributional regression. So GAM LSS models, so for where the LSS is for location, scale, and shape. And we can have like individual functions for different parameters of our posterior distribution. And so, for example, we can model the conditional mean and the conditional variance of a Gaussian model individually, and then boost components into these two things in one joint framework. I also did talk a bit about this before, so I want to go a bit more in detail here. So very often we are interested in these marginal effect plots. So very often, if we want to interpret our model, we would like to see something like, hey, if we have our feature, I don't know, x3 here, and we have our outcome y, what's kind of the marginal effect from x3 on that feature? And often would like to plot that. Yeah, and I guess then analyze and interpret that. The nice thing about component-wise boosting is that we do not have to do anything on top of the algorithm as long as we are using appropriate base learners. So if we use single features as in our base learners, so we can kind of consider each base learner as something like a wrapper around the feature representing the feature's effect on the target. We have already acknowledged that base learners can be selected more than once in the different boosting iterations, of course, usually with different parameter estimates. If that happens, usually we're not kind of done adapting our model with respect to that feature. But the nice thing is that we can then collect later at the end all of the functions of the same type with respect to a specific feature, and then collect together all their different parameterizations and add them up. We could even add up, like in the plot, the univariate base learners referring to the same feature. Well, actually, let's do this maybe step by step. So maybe we have like an iteration 1, we have an iteration 2, and an iteration 3 here in our component-wise boosting procedure. And in the first iteration, we would maybe select a spline base learner for feature 2. Then we would select something for feature 3. And then we would select something again for feature 2, maybe of the same type. If these two guys are of the same type, we can easily add up their parameter vectors, and now we get one curve for feature 2, and this would be our partial dependence curve, our marginal effect for feature 2. And for feature 3, we can do the same. So here there was just one, but maybe they're multiple. Again, we can add them up. And if we cannot add up the parameterizations because the base learners are of different types, what we can still do is add up their curves to produce one univariate curve representing the effect that that feature has on the outcome. And that's pretty nice. So we get all of that PDP stuff for free at the end, as long as we are not beginning to use base learners with interactions, effects, and so on. Yeah, well, then I guess we run into exactly the same problems as in other model classes with where more complex interactions are allowed, and then we might still have to compute stuff like PDPs in a post-hoc fashion, but this would be part of an interpretable machine learning lecture, which we also run here and have online as well. Next to these effect curves, people are usually also interested in the importance of individual features and quantitative measures for feature or variable importance. We can also compute that from component-wise boosting. So what we usually do for that is actually pretty simple. So what we do is we kind of compare the risk reduction going from iteration m-1 to iteration m for a specific feature. So let's say we are interested in, I don't know, feature x2. We would look at all of the iterations where feature x2 would actually be selected, and then compute these risk reductions here simply as the difference between previous loss and before we do that iteration and the loss after that iteration, and we sum up all of these reductions to a global reduction for that feature. Then I guess at the end maybe normalize that and take that as a quantitative measure of that feature's importance. Wrapping everything up, component-wise boosting is kind of a statistical reinterpretation of gradient boosting. It's a pretty nice procedure to fit statistical models in quite high dimensions. So people also like using that in the P much larger than N scenario, exactly because of this sparseness property. And it's a feature selection property. We discussed that if you want to really do valid inference at the end for coefficients and so on, that can be a bit more complicated, or might have to resort to bootstrapping or so on, or more complicated stuff like post-selection inference. And compared to what we studied for tree-based gradient boosting, especially with somewhat deeper trees, usually will be stronger in terms of predictive performance, but you kind of pay for that quite heavily by creating a model with a huge ensemble of semi-deep trees, which is not really interpretable anymore. I would say component-wise boosting is now situated nicely somewhere in the middle. So you have something like, I don't know, LMs or GLMs, yeah, could fit a GAM model, okay? And usually these are, yeah, this is usually not so strong in terms of predictive performance. This can be a bit better. You can also fit your GAM model through the component-wise boosting procedure. You can also kind of, or maybe I should move to the side a little bit. And then here we have stuff now like XGBoost, I don't know, neural networks, support vector machines. So many people kind of start with linear models like that, and if they fail, they kind of go directly to these types of models, and then they lose all aspects of interpretability. So if you are in such a situation, it's probably a good idea to at least run component-wise boosting as a further option, as a further, I don't know what I want to call that. I really don't want to call it a baseline. Just run it as a further alternative. Usually get stronger performance out of this because you can handle nonlinear effects at the very least for individual features, and you can really handle and can target loss functions as you like, and use this gradient descent in function space principle, and that usually gives rise to pretty aggressive loss minimization, as long as you do not need like very complicated interactions in your model. You might actually get a nice compromise model, which is still nicely interpretable, but still gives you enough predictive power to handle your data situation at hand. So this concludes this part until here. I hope you enjoyed this and you understood this. See you in the next chapter.